Recognition by Harvard for groundbreaking theoretical physics work is not something that happens through chance or popularity. It is the result of ideas that withstand intense scrutiny, ideas that contribute meaningfully to the deepest questions science can ask. In the case of Sabrina Pasterski, Harvard's recognition reflects not only her technical skill, but the unusual originality and depth of her theoretical insight. Within one of the world's most demanding academic environments, she distinguished herself by engaging with problems that most physicists avoid because of their complexity and conceptual difficulty. Harvard's physics community is built around rigorous standards. New ideas are not celebrated simply because they are novel. They must be mathematically sound, physically consistent, and capable of advancing understanding beyond what already exists. Pasterski's work met these standards early in her career. Her research focused on the structure of spacetime, quantum gravity, and the behavior of information in extreme conditions, particularly around black holes. These are not fashionable topics chosen for attention, but foundational problems that sit at the unresolved core of modern physics. What made her work stand out was the way she approached these problems. Rather than treating physics as a collection of established rules, she examined the assumptions behind those rules. Her research explored hidden symmetries in spacetime and how these symmetries might preserve information that appears to be lost in black holes. This line of inquiry directly addresses the black hole information paradox, one of the most serious conflicts between quantum mechanics and general relativity. Harvard recognized that this was not routine theoretical work, but an attempt to resolve contradictions that have challenged physicists for decades. Another reason for Harvard's recognition lies in the independence of her "Who is Sabrina Pasterski?" thinking. In many research environments, young scientists build careers by working within large teams, contributing small pieces to established programs. Pasterski followed a different path. Her work showed a rare willingness to think alone, to question dominant interpretations, and to pursue ideas even when they did not align neatly with existing frameworks. This intellectual independence is highly valued in theoretical physics, where progress often depends on reimagining the foundations rather than refining surface details. Her papers demonstrated a level of clarity and conceptual precision that caught the attention of senior physicists. Rather than relying on excessive formalism, her work emphasized physical meaning. Equations were not treated as abstract symbols, but as expressions of real processes occurring in spacetime. This ability to connect mathematics with physical intuition is one of the traits that led Harvard scholars to view her as exceptional. It suggested a mind capable of producing not just calculations but understanding. Harvard's recognition also reflects the long-term potential seen in her research. Theoretical physics advances slowly, and the true value of an idea is often revealed years after it is introduced. Paster's work opened new directions for thinking about conservation, laws, symmetry, and information at the boundaries of spacetime. Even where her ideas did not provide final answers, they reshaped how questions were asked. This influence on the intellectual landscape is one of the strongest indicators of groundbreaking work. Importantly, this recognition was not driven by public attention or media narratives. Much of Pasterski's work circulated quietly within academic circles, discussed in seminars, papers, and peer review rather than headlines. Harvard's acknowledgement came from careful evaluation by experts who understood the significance of what she was attempting. In this sense, her recognition represents the purest form of scientific validation rooted in merit rather than visibility. The environment at Harvard further amplified the importance of her contributions. Surrounded by leading physicists working on quantum field theory, cosmology, and gravity, Pasterski's ideas were tested against the highest level of expertise. That her work not only survived this environment, but earned respect within it speaks to its strength. Recognition in such a setting implies that her ideas were not only correct, but meaningful enough to influence ongoing research. Ultimately, Harvard's recognition of Sabrina Pasterski for groundbreaking theoretical physics work reflects a rare combination of qualities. It acknowledges technical excellence, conceptual originality, intellectual courage, and a focus on fundamental truth. It signals that her contributions are not confined to narrow problems, but touch the core principles that define our understanding of the universe. In recognizing her, Harvard recognized the presence of a thinker whose work belongs not just to the present moment, but to the future direction of physics itself. Exceptional intellect demonstrated from an unusually young age is not simply a story of early achievement, but a reflection of how a mind relates to ideas long before formal recognition arrives. In the case of Sabrina Pasterski, her early intellectual development revealed a pattern that later became central to her identity as a physicist, an intense curiosity about how the universe works, paired with the ability to understand complex systems intuitively rather than mechanically. From childhood, Pasterski showed an uncommon relationship with learning. She was not driven by memorization or competition, but by exploration, concepts that many encounter only after why she's called the next Einstein. Years of study, motion energy, cause, and effect were things she questioned naturally. Instead of accepting explanations at face value, she wanted to know why the rules existed and whether they could be derived from something deeper. This approach mirrors how great scientific thinkers often begin not with answers, but with persistent questions. One of the most striking indicators of her exceptional intellect was her engagement with engineering and physics at an age when most children are still being introduced to basic science. Building, experimenting, and testing ideas were not academic exercises for her. They were expressions of understanding. When she worked with machines or systems, she did not treat them as isolated objects, but as physical manifestations of underlying laws. This ability to see structure beneath complexity is a hallmark of high-level scientific thinking. Her early exposure to advanced ideas did not overwhelm her. Instead, it seemed to sharpen her focus. While many young prodigies excel by accelerating through standard material, Pasterski demonstrated something rarer: depth rather than speed. She lingered on fundamental concepts, seeking coherence rather than completion. This meant that even at a young age, she was developing the kind of conceptual framework that later allowed her to approach theoretical physics with confidence and originality. Educational institutions recognized this unusual capacity quickly. Mentors observed that she did not merely solve problems, she reframed them. When given a challenge, she often approached it from angles that were not taught, guided by intuition grounded in physical reasoning. This ability to think beyond prescribed methods is not easily taught, and its presence so early suggested a mind naturally aligned with theoretical inquiry. Another defining feature of her early intellect was independence. Pasters did not rely heavily on external validation. She pursued ideas because they made sense to her, not because they were rewarded. This independence is critical in theoretical physics, where progress often requires resisting consensus and trusting one's reasoning even when it leads into unexplored territory. Seeing this trait emerge so early reinforced the perception that her abilities were not the result of training alone, but of intrinsic cognitive orientation. Her early achievements also reflected emotional discipline alongside intellectual strength. Complex ideas can be frustrating, especially for young learners, yet she demonstrated patience and persistence. Rather than becoming discouraged by difficulty, she treated it as a signal that something meaningful lay beneath the surface. This emotional relationship with challenge is as important as raw intelligence because it sustains long-term engagement with difficult problems. As she matured academically, the foundations laid in her youth became increasingly visible. Advanced mathematical structures, abstract physical theories, and unresolved paradoxes did not appear foreign to her way of thinking. They felt like natural extensions of the questions she had been asking all along. Her early intellectual development did not burn out or plateau. It evolved, gaining precision and rigor while retaining its original curiosity-driven core. It is important to distinguish exceptional intellect from early fame. Pasterski's youth was not defined by publicity or spectacle. Instead, it was marked by quiet engagement with ideas and a steady refinement of understanding. This distinction matters because it suggests sustainability. Minds that develop in this way are less likely to depend on external pressure and more likely to continue producing meaningful work over time. In retrospect, her unusually early intellectual clarity appears less like a coincidence and more like a signal. It revealed a thinker whose relationship with physics was not learned late, but embedded from the beginning. The questions that define modern theoretical physics about space, time, and the nature of reality require exactly this kind of long-formed intuition. Her early years did not predict specific discoveries, but they revealed a way of thinking uniquely suited to confronting the deepest problems science has to offer. Contributions to quantum gravity and black hole physics place Sabrina Pasterski's work at the very edge of what modern science can currently explain. These fields are not just advanced areas of physics. They represent the unresolved heart of our understanding of reality. Quantum gravity seeks to unite Harvard and early achievements, two of the most successful theories ever created. Quantum mechanics, which governs the smallest scales of nature, and general relativity, which describes gravity and the structure of spacetime. Black hole physics sits precisely at the intersection of these theories, where both must operate simultaneously and where their contradictions become impossible to ignore. Pasterski's contributions are significant because she does not approach these problems as isolated technical puzzles. Instead, she treats them as conceptual contradictions that demand new ways of thinking. Black holes, once thought to be simple cosmic objects that swallow everything, have become laboratories for testing the limits of physics. According to classical relativity, nothing escapes a black hole. According to quantum theory, information cannot be destroyed. When these ideas collide, the result is a paradox that has troubled physicists for nearly half a century. Pasterski's work engages directly with this conflict. One of her most influential contributions involves the role of symmetry in spacetime. Symmetry is a powerful concept in physics, often linked to conservation laws such as energy or momentum. Pasters explored previously overlooked symmetries near the boundaries of spacetime, particularly around black holes. Her research suggested that information about particles falling into a black hole might be encoded in subtle gravitational degrees of freedom at its edge. This idea challenges the assumption that black holes erase all traces of what enters them. In quantum gravity, spacetime itself becomes a dynamic quantum object rather than a smooth background. Pasterski's work helped clarify how quantum information might be preserved even when classical descriptions fail, by examining how gravitational fields respond to particles at extreme limits. She provided new mathematical structures that allow physicists to track information in ways that were not previously considered. These insights do not claim to fully solve quantum gravity, but they reshape the landscape in which solutions might emerge. Her contributions also stand out for their restraint. Rather than proposing grand speculative theories disconnected from established physics, Pasterski works within known frameworks, extending them carefully into new regimes. This approach lends credibility to her ideas because they respect what is already known while revealing its limitations. In black hole physics, where speculation can easily outrun evidence, this balance is especially valuable. Another important aspect of her work is how it bridges communities within physics. Quantum gravity research often divides into competing camps, each with its own language and assumptions. Pasterski research speaks across these divisions by focusing on universal principles such as symmetry, conservation, and information. This has allowed her ideas to influence researchers working in string theory, quantum field theory, and gravitational physics alike. Her contributions also changed how physicists think about the edges of spacetime. Traditional models treated boundaries as mathematical conveniences, but Pasterski's work emphasized their physical significance. She showed that what happens at these boundaries may carry essential information about the entire system. This perspective has implications not only for black holes but also for cosmology and the early universe where similar boundary conditions arise. Importantly, her influence extends beyond specific equations or models. By reframing questions about black holes in terms of information and symmetry, she helped shift the conceptual focus of the field. This kind of contribution is rare because it does not just add to knowledge, it reorganizes it. Physicists began asking different questions as a result of her work, which is one of the strongest indicators of lasting impact in the broader context of physics. Paster's contributions to quantum gravity and black hole physics represent a step toward coherence in a fragmented theoretical landscape. While a complete theory of quantum gravity remains elusive, her work provides tools and insights that bring that goal closer. It demonstrates that progress does not always come from bold declarations, but from precise, deeply reasoned ideas that illuminate hidden connections within the universe. Through these contributions, Sabrina Pasterski established herself not simply as a participant in one of physics' hardest problems, but as a thinker capable of shaping how that problem is understood in fields defined by uncertainty and contradiction. Her work offers structure, clarity, and a path forward qualities that define truly meaningful scientific advancement. Work connecting general relativity with quantum mechanics represents one of the most ambitious goals in all of science because it attempts to reconcile two theories that are each extraordinarily successful yet fundamentally incompatible. General relativity describes gravity as the curvature of spacetime caused by mass and energy functioning seamlessly on cosmic scales. Quantum mechanics governs the behavior of particles and forces at the smallest measurable scales where uncertainty and probability dominate. For decades, physicists have known that both theories are correct within their domains, but they break down when applied together. Sabrina Pasterski's work enters precisely this fragile black holes and quantum gravity boundary. Rather than attempting to force one theory to dominate the other, Pasterski focuses on understanding how their principles might coexist. Her research explores how quantum information behaves in curved spacetime, particularly in extreme gravitational environments such as black holes. These settings demand that both general relativity and quantum mechanics be applied simultaneously, revealing their contradictions in the clearest possible way. By working in these environments, she addresses the problem at its most fundamental level. A central theme in her work is the nature of information. Quantum mechanics insists that information is conserved, while classical interpretations of general relativity suggest that information can be lost behind event horizons. Pasters examines how subtle gravitational effects and symmetries may preserve quantum information in ways that classical descriptions overlook. This approach does not discard either theory, but instead seeks hidden structures that allow them to remain consistent with one another. Her work often focuses on the boundaries of spacetime, regions where classical geometry begins to fail, and quantum effects become unavoidable. In general relativity, boundaries are often treated as mathematical abstractions. Pasterski's insight was to treat them as physically meaningful. She showed that these boundaries can store information through soft gravitational modes, offering a potential mechanism by which quantum mechanics and gravity can communicate without contradiction. Another important aspect of her work is the use of symmetry as a bridge between theories. Symmetry principles play a central role in both quantum mechanics and general relativity, but they are applied differently in each framework. Pasterski identified ways in which certain symmetries persist even in extreme gravitational settings. These symmetries act as anchors, allowing quantum properties to survive in curved spacetime without being erased by gravitational collapse. What distinguishes her contribution is not the creation of a complete unified theory, but the identification of precise points of contact between the two frameworks. She isolates specific situations where quantum and gravitational effects overlap and analyzes them with exceptional clarity. This incremental yet profound approach contrasts with more speculative attempts at unification and has earned respect for its rigor. Her work also has implications beyond black holes. Early universe cosmology, where spacetime was intensely curved and quantum effects dominated, faces similar theoretical challenges. The methods and insights developed by Pasterski provide tools for understanding how the universe may have evolved from a quantum-dominated state into the classical cosmos observed today. In this sense, her work connects not only theories but eras of cosmic history. Another defining feature of her research is its conceptual discipline. She avoids unnecessary assumptions and resists simplifying complex problems in ways that obscure their true nature. This discipline is crucial when working at the interface of two powerful theories, where small conceptual errors can lead to large inconsistencies. Her careful reasoning ensures that each step respects the core principles of both quantum mechanics and general relativity. By focusing on information, symmetry, and boundaries, Pasterski contributes to a growing view that the conflict between quantum mechanics and gravity may not require abandoning either theory, but rather reinterpreting how they interact. This perspective has influenced how other physicists frame the problem, encouraging approaches that prioritize consistency and physical meaning over mathematical complexity alone. In the broader narrative of physics, work connecting general relativity with quantum mechanics represents a slow, deliberate effort rather than a sudden revolution. Paster's contributions exemplify this process. She does not claim final answers, but she illuminates pathways that were previously obscured. Doing so, she brings coherence to one of science's deepest challenges and strengthens the possibility that a unified understanding of nature is not only desirable, but achievable. Research on Hawking radiation and the information paradox places Sabrina Pasterski at the center of one of the most profound crises in modern physics. Hawking radiation, first proposed in the 1970s, revealed that black holes are not completely black. Instead, quantum effects near the event horizon allow them to emit radiation and slowly lose mass over time. This discovery was revolutionary, but it created a serious problem. If a black hole eventually evaporates, what happens to the information carried by everything that fell into it? According to quantum mechanics, information can never be destroyed. According to classical interpretations of black holes, it disappears forever. This contradiction is known as the black hole information paradox. Pasterski's work approaches this paradox not as a mystery to be solved by speculation, but as a structural inconsistency that must be addressed through careful analysis. She examines how Hawking radiation is produced and what it can carry with it. Rather than treating the radiation as purely thermal and random, her research explores the possibility that it encodes subtle information about the black hole's past. This idea challenges the traditional view that Hawking radiation is entirely featureless. A key aspect of her contribution lies in rethinking the event horizon itself. Classical physics treats the event horizon as a clean boundary, a point of no return. Pasterski's work suggests that this boundary is more complex when quantum effects are taken into account. She investigates how soft gravitational and quantum modes near the horizon may act as carriers of information, preserving traces of what falls into the black hole rather than erasing it. Her research builds on the idea that conservation laws extend even to extreme gravitational environments. In quantum theory, every interaction leaves an imprint. Paster's work suggests that black holes may obey similar rules, with information being redistributed rather than destroyed. Hawking radiation, in this view, becomes part of a larger information-preserving process rather than a mechanism of loss. One of the strengths of her approach is its grounding in established physics. She does not discard Hawking's original insights, nor does she reject the framework of general relativity. Instead, she asks whether the assumptions used to interpret Hawking radiation were incomplete. By carefully analyzing the symmetries and conservation principles at play, She identifies overlooked mechanisms that could reconcile radiation with information conservation. Her work also addresses the psychological challenge of the paradox. For decades, physicists debated whether quantum mechanics or general relativity would have to give way. Pasterski's research supports a third possibility, that the paradox arises from an incomplete understanding of how these theories interact at boundaries. This reframing shifts the focus from choosing a winner to uncovering missing structure. Another why she avoids academia important contribution is how her ideas influence the interpretation of black hole evaporation. If information is preserved, then the final stages of a black hole's life are not meaningless noise, but a complex process through which information is released back into the universe. This perspective has implications for the arrow of time, entropy, and the fundamental nature of irreversibility in physics. Her work also resonates beyond black holes. The information paradox forces physicists to confront the nature of reality at its most extreme. If information can survive a black hole, then the universe may be more orderly and predictable at fundamental levels than previously thought. Pasterski's research contributes to this broader philosophical shift by reinforcing the idea that the laws of physics remain consistent even under extreme conditions. Importantly, her influence is measured not by dramatic claims but by how her ideas reshape discussion. Researchers now routinely consider information-carrying mechanisms near horizons as legitimate components of black hole physics. This change in perspective reflects the impact of careful, disciplined work rather than sensational breakthroughs. In the ongoing effort to understand Hawking radiation and resolve the information paradox, Pasterski's research stands as a model of clarity and restraint. She treats one of physics' most troubling contradictions not as a dead end, but as a guide pointing toward deeper principles. By doing so, she brings coherence to a problem that once seemed to threaten the very foundations of modern science. Known for deep original thinking rather than academic publicity, Sabrina Pasterski represents a rare figure in modern science where visibility often competes with substance. In an era dominated by conferences, media profiles, and rapid publication cycles, her reputation has grown quietly, shaped almost entirely by the strength of her ideas. This distinction is not accidental. It reflects a deliberate focus on understanding rather than recognition, and it has become one of the defining features of her scientific identity. Pasterski's approach to physics emphasizes depth over volume. She does not aim to produce a large number of papers or to align her work with popular trends. Instead, she concentrates on foundational questions that require long periods of thought and refinement. This kind of work does not lend itself easily to publicity because its value is often subtle and becomes clear only to those deeply engaged with the field. Yet within theoretical physics, this depth is precisely what earns lasting respect. Her original thinking is evident in how she frames problems. Rather than starting from established methods and extending them slightly, she often begins by questioning assumptions that others take for granted. This habit allows her to identify gaps in understanding that may be invisible to those working within conventional frameworks. It is a risky approach because challenging assumptions can isolate a researcher from mainstream discussions. Pasterski accepts this risk, guided by intellectual coherence rather than external validation. Academic publicity tends to reward clarity of narrative and immediate impact. Deep theoretical work, by contrast, often advances through small conceptual shifts that lack dramatic presentation. Pasterski's ideas fall into this second category. They reshape how physicists think about information, symmetry, and spacetime without announcing themselves as revolutions. This quiet influence explains why her name circulates strongly within expert circles while remaining relatively absent from popular science media. Another reason she avoids publicity is her commitment to precision. Simplifying complex ideas for broad audiences often requires sacrificing nuance. Pasterski appears unwilling to do this at the cost of accuracy. Her work demands careful interpretation, and she seems to prefer discussion in environments where ideas can be examined rigorously rather than compressed into headlines. This choice reinforces her reputation as a thinker who prioritizes truth over attention. Her intellectual independence is closely linked to this stance. Publicity can create pressure to defend positions or repeat ideas beyond their natural scope. By staying largely outside the spotlight, Pasterski preserves the freedom to revise her thinking as new insights emerge. This flexibility is essential in theoretical physics, where progress often requires abandoning earlier interpretations. Her low-profile approach allows her ideas to evolve without the burden of public expectation. Within academic communities, this behavior signals confidence. Scientists who rely on publicity often seek external confirmation of their work's importance. Paster's relative silence suggests that her motivation lies elsewhere. She appears driven by the internal standards of the discipline rather than by metrics of visibility. This attitude resonates with senior physicists who recognize that the most enduring contributions often come from those least concerned with recognition. Her deep originality also manifests in the way she engages with existing literature. Instead of treating previous work as a fixed authority, she reads it as a conversation open to reinterpretation. She connects ideas across subfields, finding relationships that others may overlook because they remain confined to narrow specialties. This integrative thinking allows her to generate insights that feel both unexpected and inevitable once articulated. The contrast between her influence and her public presence highlights a broader tension in modern science. As research becomes increasingly competitive, the ability to attract attention can sometimes overshadow the ability to think deeply. Pasterski's career offers a counterexample. It demonstrates that originality and rigor can still command respect even without constant visibility, provided the work addresses questions of genuine importance. Over time, this approach may prove to be her greatest strength. Scientific recognition that arises from sustained intellectual contribution tends to endure longer than recognition built on visibility alone. Ideas rooted in deep understanding continue to influence future research even when their originators remain in the background. Pasterski's work appears positioned in this tradition, ultimately being known for deep original thinking rather than academic publicity is not an absence of presence, but a different kind of presence. It reflects a commitment to ideas that speak quietly but persistently. In a field where lasting progress depends on conceptual clarity and intellectual courage, this quality may matter more than any headline, and it explains why her work continues to command serious attention among those who truly understand its significance. Comparison to Einstein based on conceptual innovation, not fame, highlights the unique way Sabrina Pasterski has been recognized within the scientific community. Unlike many public figures whose reputations are amplified by media attention or social prominence, the association with Einstein is rooted entirely in the originality and depth of her ideas. This distinction is critical because Einstein himself was not first famous for his public persona, but for his ability to reconceptualize fundamental physics in ways that transform the field. Similarly, Pasterski's recognition stems from her capacity to question assumptions, explore hidden structures in established theories, and develop new frameworks that illuminate unresolved problems. Einstein's revolutionary work was not merely technical. It involved rethinking the foundations of space-time and energy. Paster's operates in a similar conceptual space, although the context of her work is the complex interface between general relativity and quantum mechanics, particularly in the study of black holes and quantum gravity. In both cases, the comparison is not about achieving celebrity or popularity, but about demonstrating the rare intellectual ability to see beyond conventional limits and imagine the laws of the universe in fundamentally new ways. The parallel to Einstein is also reflected in her approach to problems. Pasterski, like Einstein, focuses on understanding principles rather than accumulating calculations or applying formulas mechanically. She seeks the underlying logic that governs physical phenomena, searching for simplicity within complexity. This kind of conceptual innovation requires the ability to think independently, question dominant paradigms, and remain undistracted by external pressures, qualities that both she and Einstein share. Importantly, the comparison does not suggest that her work is identical to Einstein's or that she will replicate his achievements. Physics has evolved dramatically since Einstein's time, and the questions she addresses, such as the information paradox in black holes, how her ideas challenge physics, Hawking radiation, and the role of symmetry in quantum gravity, are specific to the contemporary scientific landscape. What aligns her with Einstein is the methodological spirit, approaching the most difficult problems with original, principled reasoning rather than incremental adjustments to existing frameworks. Her recognition as the next Einstein by peers and commentators in the scientific community underscores the rarity of her contributions. Einstein's contemporaries noted his capacity for intuitive thought, his willingness to challenge orthodoxy, and his focus on conceptual coherence. Pasters demonstrates similar traits. She does not seek attention through media appearances or simplified explanations, but through work that withstands rigorous scrutiny and has the potential to reshape foundational understanding. The comparison emphasizes substance over spectacle. Another dimension of this parallel is the way both thinkers influence the questions posed in physics. Einstein's theories altered not only the answers but the very framing of problems, prompting scientists to think differently about space, time, and energy. Pasterski's contributions, particularly regarding black holes and quantum information, similarly encourage the scientific community to reconsider how information behaves in extreme environments. Her work reframes long-standing paradoxes, opening new pathways for research and discussion. The focus on conceptual innovation also explains why the comparison is not a matter of public opinion. Einstein's fame grew after the recognition of his ideas' importance, not before. Likewise, Pasterski's work has been assessed on its intellectual merit within expert circles independent of media narratives or popular trends. This emphasizes that the next Einstein label in her case is a recognition of thought leadership rather than personal branding. Conceptual innovation requires patience and persistence. Many of Pasterski's insights developed over years of careful study, reflection, and iteration. Like Einstein, she demonstrates that groundbreaking science is often the product of sustained engagement with difficult questions rather than rapid or superficial work. This long-term commitment to deep thinking reinforces the validity of the comparison, highlighting the seriousness with which her contributions are regarded. In addition, her approach illustrates the transformative power of curiosity-driven research. Einstein's breakthroughs arose from asking questions that others overlooked or dismissed. Pasterski similarly pursues questions that are often considered too abstract or difficult, such as how information survives in black holes or how symmetries constrain space-time behavior. By addressing these fundamental questions, she positions herself in the tradition of revolutionary thinkers whose work changes the lens through which science views the universe. Ultimately, the comparison to Einstein based on conceptual innovation underscores that her recognition is rooted in intellectual courage, originality, and the ability to reshape thinking in physics. It is not about fame or external accolades, but about demonstrating the rare capacity to see beyond accepted paradigms and offer new ways of understanding reality. In this light, Pasterski's work exemplifies the qualities that define transformative scientific contributions, aligning her with the spirit of Einstein's legacy in a modern context. Published influential papers early in her academic career, Sabrina Pasterski established herself as a remarkable presence in the world of theoretical physics at a stage when most students are still learning the foundational tools of their discipline. Early publication in the scientific world is not merely a matter of producing work. It reflects the ability to formulate questions that are both meaningful and approachable, to develop methods that are rigorous and reproducible, and to communicate ideas clearly to a community of expert peers. Pasterski's early success in this regard highlights both her extraordinary intellectual maturity and her capacity to contribute significantly to ongoing research conversations from a young age. Her papers addressed some of the most challenging areas in modern physics, including black hole dynamics, quantum information, and the interplay between general relativity and quantum mechanics. These topics are not only mathematically sophisticated but conceptually demanding. Producing work in these areas that meets the high standards of peer review is a testament to her deep understanding of the underlying principles and her ability to navigate the complex literature that surrounds them. Each paper she published was evaluated rigorously by experts, not merely for correctness, but for the significance of the ideas, their potential to advance understanding, and their originality. The early nature of her publications also reflects her proactive approach to research. Rather than waiting for formal opportunities or structured guidance, she sought out challenging problems independently. This self-directed approach allowed her to explore questions that were not only technically difficult but intellectually stimulating, providing insights that often challenged conventional thinking. Her willingness to tackle these problems at an early stage demonstrates not just talent, but also the confidence to engage with ideas that even senior researchers find daunting. Moreover, the influence of her early publications extends beyond the number of papers or citations. They served as entry points for other researchers to explore new directions in theoretical physics by clearly articulating her ideas and the reasoning behind them. She provided tools and conceptual frameworks that colleagues could adopt, test, or expand upon. This type of contribution is particularly significant because it accelerates collective progress in fields that are often slow-moving due to their complexity. Another important aspect of publishing influential work early is the demonstration of intellectual independence. In academia, many young researchers contribute to established projects under close supervision, producing work that is valuable but constrained by the direction set by senior mentors. Pasters, by contrast, demonstrated the ability to identify original questions, develop methodologies, and articulate conclusions with minimal reliance on external guidance. This independence is a hallmark of researchers who later make transformative contributions to their fields. Her early publications also highlight her skill in bridging abstract theory and concrete analysis. While some theoretical work can remain entirely speculative, Paster's papers often connected abstract concepts to testable implications or to frameworks already familiar to the scientific community. This ability to ground high-level theoretical ideas in precise reasoning makes her work more accessible to other physicists and increases its potential impact. The rigorous peer review process further underscores the significance of her achievements. Scientific publication is not a measure of self-promotion. It is a rigorous evaluation by knowledgeable peers who critically assess clarity, methodology, accuracy, and originality. That Pasterski successfully navigated this process at such an early stage indicates that her work met the highest standards of intellectual scrutiny. It is a clear signal that her contributions were taken seriously by the community and were seen as valuable additions to the scientific literature. Publishing influential papers early also positions a researcher to shape the discourse in their field. Theoretical physics is often driven as much by the framing of questions as by the solutions proposed by introducing new perspectives and highlighting overlooked connections. Her early work encouraged other scientists to reconsider assumptions, explore new avenues, and refine their models. This impact achieved before the typical career milestones of post-doctoral positions or faculty appointments illustrates the exceptional nature of her contributions. Finally, the significance of early influential publications extends beyond immediate academic recognition. They build a foundation for long-term impact, signaling a trajectory in which the researcher is capable of sustained, meaningful contributions. In Pasterski's case, her early work established a pattern of originality, rigor, and independence that continues to define her career. It demonstrates that transformative thinking in physics is not solely a matter of age or formal status, but of intellectual vision and disciplined execution. Her early publications are thus a testament not only to her exceptional talent, but also to the enduring influence she brings to the field of theoretical physics. Focus on fundamental laws of the universe has been a defining characteristic of Sabrina Pasterski's work, distinguishing her from many contemporary physicists whose research often emphasizes incremental findings or applied results. Her investigations are not limited to solving isolated problems or producing technical refinements. Instead, they aim at understanding the principles that govern the universe at its most basic level. This orientation reflects a deep commitment to uncovering the structures and symmetries underlying physical reality, and it is this dedication that has drawn comparisons to some of the greatest thinkers in the history of physics. Pasterski's approach begins with curiosity about the very building blocks of nature. She is concerned with questions that probe the foundations of space, time, and matter, exploring how these elements interact under extreme conditions. In particular, she examines how information behaves in systems governed simultaneously by quantum mechanics and general relativity, such as black holes. These investigations go beyond mere calculation. They require rethinking what the laws of physics imply about the universe and how seemingly contradictory principles can coexist. A focus on fundamental laws also manifests in her exploration of symmetry and conservation. Symmetries in physics are not just aesthetic. They correspond to conservation laws which dictate that certain quantities, energy, momentum, charge remain constant under specific conditions. Pasterski's research investigates subtle symmetries that may exist even in extreme or previously overlooked contexts such as near the event horizons of black holes. By identifying these symmetries, she provides a framework for understanding how fundamental laws operate under circumstances where traditional methods fail. This orientation toward the fundamentals also influences her methodological choices. Rather than relying on complex simulations or phenomenological models alone, she employs a combination of rigorous mathematical analysis and physical reasoning. Her work emphasizes clarity, seeking to reveal the principles behind observed phenomena rather than merely describing patterns. In doing so, she follows a tradition in theoretical physics that values conceptual understanding as much as technical correctness, emphasizing the why as much as the how. Ostrowska's focus on the fundamental laws is particularly relevant in the context of black hole physics and quantum gravity, fields where intuition derived from everyday experience is often misleading. In these extreme environments, familiar concepts such as locality, causality, and the flow of time are challenged. By grounding her work in the underlying principles of physics, she navigates these conceptual hazards, proposing ways to reconcile apparent contradictions and impact on future science to understand how universal laws persist even under extreme conditions. Her work also highlights the importance of abstraction in theoretical physics. While experimental results and empirical data are essential, fundamental law-focused research often requires reasoning about hypothetical scenarios or extreme conditions that cannot yet be tested directly. Pasterski's ability to reason rigorously about these abstract situations demonstrates both intellectual creativity and precision. She constructs theoretical frameworks that can guide future experiments, providing predictions and principles that remain valid across a range of possible conditions. Another aspect of her focus on fundamental laws is its longevity and universality. Work aimed at understanding basic principles tends to have enduring relevance because the laws themselves are constant even as technologies and applications evolve. Pasterski's contributions thus have the potential to influence physics for decades, shaping how future generations understand the universe. This is in contrast to more specialized or applied work, which may lose relevance as methods and technologies change. Her attention to fundamental laws also informs the questions she chooses to address. Instead of focusing on immediate or localized problems, she seeks issues that, if resolved, would have broad implications. For example, understanding how information behaves in black holes does not only illuminate one astronomical phenomenon. It challenges the core assumptions of quantum mechanics and general relativity alike. By tackling such questions, she positions her work at the center of debates about the structure of reality itself. The clarity and depth of her focus have earned her recognition within the scientific community. Experts note that her work does not merely add incremental knowledge, but reshapes how certain questions are framed, opening new avenues of inquiry. This impact is a hallmark of research that addresses the fundamentals. It influences not just the answers but the way future scientists think about the problems themselves. Ultimately, Paster's focus on the fundamental laws of the universe reflects a vision that transcends immediate results. It embodies the intellectual rigor, conceptual daring, and disciplined inquiry that define transformative scientific work. By concentrating on the principles that govern all phenomena, she contributes to the ongoing effort to create a coherent and comprehensive understanding of the cosmos, ensuring that her work resonates deeply within the history and future of physics. Avoids media spotlight despite global scientific attention. Sabrina Pasterski represents a rare model of intellectual focus in an era where visibility and public recognition often dominate perceptions of success. While many prominent scientists are known as much for their interviews, social media presence, and public appearances as for their work, Pasterski has deliberately maintained a low profile, letting her research speak for itself. This choice reflects a deep commitment to scientific integrity and a belief that the significance of her contributions should be measured by their intellectual impact rather than by public acclaim. From the beginning of her career, Pasterski demonstrated a preference for quiet, rigorous engagement over media exposure. Despite early recognition for her extraordinary talent and the inevitable curiosity that surrounded her trajectory, she did not seek to capitalize on public attention. Instead, she focused on the demands of her research, exploring complex questions in theoretical physics such as black hole information, quantum gravity, and the interface between quantum mechanics and general relativity. By maintaining this focus, she ensured that her work could develop without being shaped or distorted by the pressures of publicity. Her avoidance of the media spotlight is also strategic in maintaining the quality and integrity of her scientific work. Public attention can often create external pressures to simplify complex ideas, to produce results quickly, or to frame research in ways that are more easily digestible to non-spacists. While such pressures may benefit public understanding or career advancement, they can also compromise the depth and precision that theoretical physics demands. Pasterski's choice to minimize public exposure allows her the freedom to explore ideas fully, to iterate, refine, and question without the distractions of external expectations. This low-profile approach has also contributed to her credibility within the scientific community. Colleagues and senior researchers recognize that her motivations are intrinsic and intellectual rather than performative. By avoiding the media spotlight, she demonstrates that her work is driven by curiosity and commitment to truth rather than by the desire for fame or recognition. This attitude fosters respect, particularly in fields such as theoretical physics, where the ultimate value of contributions is measured not by visibility, but by conceptual rigor and the ability to influence ongoing research. Her discretion has not prevented her from gaining global attention within scientific circles. On the contrary, her work has been widely discussed and cited among experts, emphasizing that meaningful impact in science often arises independently of public awareness. Her papers on black holes, information conservation, and quantum gravity have circulated within peer-reviewed journals, seminars, and conferences, reaching the right audience. Scientists capable of evaluating, building upon, and applying her ideas. This selective attention ensures that the recognition she receives is substantive rather than superficial. Furthermore, avoiding the media spotlight enables her to work in intellectual isolation when necessary. Theoretical physics often requires extended periods of concentration, abstract reasoning, and the freedom to pursue unconventional ideas. Public scrutiny can interfere with this process, introducing pressures to justify work prematurely or defend it against misinterpretation. Pasterski's approach allows her to navigate these challenges on her own terms, fostering an environment where innovation is guided by logic and insight rather than by perception. Her choice also reflects a philosophical understanding of science itself. True scientific progress depends on rigorous inquiry and critical evaluation, not on popularity. By prioritizing research over publicity, she aligns herself with the tradition of physicists, whose lasting contributions were recognized primarily for their intellectual merit. In this context, avoiding the spotlight is not a lack of ambition. It is a conscious strategy to preserve the integrity and depth of her work. The global attention she has nonetheless received highlights an important balance. Extraordinary talent and groundbreaking research will naturally attract recognition, even without self-promotion. Pasterski's trajectory demonstrates that it is possible to gain respect and influence in the scientific community without engaging in the performative aspects of fame. Her reputation is therefore rooted in the strength of her ideas, the originality of her insights, and the clarity of her reasoning. Ultimately, by avoiding the media spotlight despite worldwide attention, Pasterski exemplifies a model of scientific dedication that prioritizes thought over spectacle. Her work continues to shape discussions in theoretical physics, influence ongoing research, and inspire the next generation of scientists, proving that profound intellectual contributions do not require public theatrics to leave a lasting impact. Her example reinforces the principle that in science substance ultimately outweighs visibility, and that true recognition arises from the enduring value of ideas. Emphasis on ideas that reshape core physics frameworks defines the distinctive impact of Sabrina Pasterski's work. Unlike research that adds incremental refinements to existing theories, her investigations target the foundational principles that govern the universe, seeking to reinterpret and reorganize established frameworks rather than merely extend them. This approach is significant because theoretical physics often progresses through subtle shifts in perspective by questioning assumptions, identifying overlooked symmetries, or proposing new conceptual tools. Researchers like Pasterski influence the way the scientific community approaches problems at the most fundamental level. Her work often focuses on the intersection of quantum mechanics and general relativity, two frameworks that individually describe vast portions of physical reality, but resist unification. These frameworks form the pillars of modern physics, yet their underlying principles sometimes appear contradictory. For instance, classical general relativity suggests that black holes destroy information, while quantum mechanics demands its preservation. By investigating such paradoxes, Pasterski does not merely solve isolated problems. She challenges the conceptual coherence of the frameworks themselves, prompting physicists to reconsider foundational assumptions about space, time, information, and causality. A central aspect of her impact is the role of symmetry in reshaping physical understanding. Symmetries in physics are not just mathematical conveniences. They encode deep conservation laws that govern energy, momentum, and information. Pasterski's research highlights previously unappreciated symmetries near boundaries of spacetime, such as at the edges of black holes, which may play a critical role in preserving information and maintaining consistency between quantum mechanics and general relativity. By illuminating these structures, she provides a new lens through which long-standing problems can be addressed, altering the conceptual landscape of physics rather than simply adding technical results. Her influence extends to the black hole information paradox, one of the most challenging puzzles in modern physics. By examining how quantum information might survive interactions with extreme gravitational fields, she reframes the problem, suggesting mechanisms through which black holes could encode or release information. This approach does more than solve a single puzzle. It reshapes how scientists think about the interaction of fundamental principles across theories, opening the door to new interpretations and lines of inquiry that may ultimately unify disparate aspects of physics. Another defining feature of Paster's work is its ability to bridge multiple subfields of theoretical physics. Traditionally, specialists in quantum mechanics, general relativity, or cosmology often operate within their own frameworks using distinct assumptions and methods. Her research, however, identifies universal principles such as symmetry, conservation, and information retention that connect these areas. By doing so, she not only advances understanding in specific domains, but also reshapes the broader architecture of theoretical physics, influencing how problems are formulated across disciplines. Her approach demonstrates the importance of conceptual clarity over technical volume. Many scientific contributions are measured by the number of calculations or data points produced. But Pasterski prioritizes conceptual insight. Each idea she develops is intended to reveal relationships and structures that previously went unnoticed, clarifying the foundational logic of physical laws. This focus ensures that her work does not merely extend existing frameworks, but actively challenges and refines them. The effect of her research is also pedagogical, shaping how new generations of physicists approach core problems. By emphasizing principles and conceptual coherence, she encourages a methodology that prioritizes deep understanding over superficial mastery of techniques. This cultural influence within the scientific community helps ensure that her contributions will persist not only through the content of her work, but through the way it transforms thinking and problem-solving approaches. Her emphasis on reshaping core frameworks is evident in the careful balance between innovation and rigor. Paster's does not propose radical changes without justification. Her insights are firmly rooted in established physics and mathematical reasoning. This disciplined approach increases the credibility of her ideas, making them influential within a field that requires extraordinary precision and logical consistency. Another dimension of her impact lies in the cumulative nature of her contributions. Each insight builds upon a careful reconsideration of fundamental laws, revealing connections between previously disconnected areas of physics. Over time, this accumulation of conceptual restructuring alters the way scientists view fundamental questions, demonstrating that reshaping frameworks is a gradual process that requires depth, persistence, and originality. By focusing on ideas that reshape core frameworks, Pasterski exemplifies the role of a transformative thinker in theoretical physics. Her work extends beyond immediate results to influence the conceptual tools and questions that guide future research. In doing so, she contributes not just answers, but new ways of thinking, reinforcing the principle that lasting scientific impact arises from the ability to reorganize understanding, illuminate hidden structures, and inspire novel approaches to enduring problems in physics. Represents a new generation of theoretical physicists. Sabrina Pasterski embodies a shift in how complex scientific inquiry is approached in the modern era. Unlike traditional trajectories in physics, which often emphasize hierarchical mentorship, narrowly defined specialties, and incremental contributions, this new generation is characterized by intellectual independence, interdisciplinary perspective, and a willingness to engage with foundational questions from a fresh vantage point. Pasterski's career exemplifies these traits, showing how emerging physicists can challenge established frameworks while simultaneously integrating deep knowledge across multiple domains. From the outset of her career, Pasterski demonstrated a propensity to work independently, identifying problems and exploring them without relying solely on conventional guidance. This independence is emblematic of a broader trend among modern theoretical physicists who increasingly combine rigorous formal training with self-directed inquiry. For Pasterski, this means tackling some of the most conceptually challenging areas in physics: black hole information paradoxes, quantum gravity, and the interplay between relativity and quantum mechanics. At a stage when many researchers are still building foundational expertise, her ability to contribute meaningfully at this level illustrates the potential for new generations of scientists to make early and substantive impacts on their fields. Another defining feature of this generation, as exemplified by Pasterski, is a comfort with cross-disciplinary thinking. While traditional research often confines scientists to narrow subfields, the emerging cohort sees connections between areas that were previously considered distinct. Pasterski's work bridges quantum mechanics, general relativity, and cosmology, highlighting symmetries and conservation laws that operate across these domains. This integrative perspective allows for the identification of patterns and principles that may remain invisible to researchers operating within more rigid boundaries, fostering conceptual breakthroughs that can reshape entire areas of physics. Pasterski's approach also emphasizes conceptual clarity over superficial productivity. In a research culture increasingly influenced by metrics such as publication counts or citation indices, she represents a generation that values depth, rigor, and foundational understanding above external markers of achievement. Her work is characterized by careful reasoning, precise mathematics, and a commitment to questions that touch the core of physical reality. This prioritization signals a philosophical shift in scientific culture, one that balances innovation with intellectual integrity. A further characteristic of this new generation is adaptability. Physics today is a rapidly evolving field with advances in computation, experimental techniques, and theoretical frameworks continually reshaping what is possible. Pasterski exemplifies the ability to navigate these changes, applying classical analytical methods alongside modern conceptual tools to tackle problems that straddle multiple theoretical regimes. Her success demonstrates how contemporary physicists can leverage both tradition and innovation to address the most challenging questions about the universe. Her career also illustrates the role of early engagement and intellectual curiosity in shaping modern, scientific trajectories. Many in this emerging generation, like Pasterski, cultivate deep expertise from a young age, but they combine it with a willingness to question authority, explore unconventional ideas, and take intellectual risks. This combination of early mastery and creative independence allows them to contribute meaningfully to ongoing debates, challenge established assumptions, and influence the evolution of scientific thought in ways that were less common in previous generations. Additionally, this generation places a strong emphasis on ideas over recognition, a trait evident in Pasterski's avoidance of media attention and her focus on rigorous research. Unlike earlier eras in which visibility often correlated with influence, her example demonstrates that substantive contributions can define one's place in the field, even in the absence of public acclaim. This approach encourages a culture in which merit and conceptual originality are valued over spectacle, fostering an environment where complex long-term problems receive the careful attention required. Pasterski's work also highlights the increasing global connectivity of this new generation. Knowledge sharing through online collaboration, access to extensive computational resources, and engagement with international research networks allows emerging physicists to operate at a level of sophistication that transcends traditional institutional boundaries. Her contributions are part of a broader movement in which ideas rather than location or affiliation alone define influence within the scientific community. Moreover, this generation is defined by its willingness to tackle questions previously considered too abstract or difficult. Pasterski's research into black hole information, quantum gravity, and fundamental symmetries demonstrates an intellectual courage to confront problems that challenge both theory and intuition. This willingness to engage with the extreme edges of understanding is a defining feature, suggesting that the next wave of theoretical physics will continue to expand the boundaries of knowledge rather than settle for incremental progress. Ultimately, Sabrina Pasterski represents a new generation of theoretical physicists because she embodies intellectual independence, interdisciplinary fluency, conceptual depth, and a willingness to address the most fundamental questions in physics. Her career exemplifies how emerging scientists can reshape research culture, approach long-standing problems with fresh perspectives, and contribute lasting insights to the field. Through her work, this generation signals a continuation of physics as a discipline, driven not by routine, but by curiosity, rigor, and transformative ideas that push the limits of human understanding. Pioneering research on space-time symmetries represents one of Sabrina Pasterski's most notable contributions to theoretical physics, addressing some of the deepest questions about how the universe preserves information and maintains consistency under extreme conditions. Symmetry, a foundational concept in physics, refers to invariance under certain transformations, changes in space, time, or other physical parameters that leave the essential properties of a system unchanged in both classical and quantum physics. Symmetries are directly linked to conservation laws governing energy, momentum, angular momentum, and more. Pasterski's work explores previously overlooked or subtle symmetries in spacetime, particularly around black holes and other extreme gravitational environments, revealing how these symmetries may play a critical role in resolving long-standing paradoxes. Her investigations focus on the boundaries of spacetime, regions where classical intuition often breaks down and where quantum effects become significant. Traditional treatments of black holes and cosmological horizons considered boundaries primarily as mathematical constructs. Paster's insight was to treat these boundaries as physically meaningful, capable of encoding information and influencing the dynamics of the system as a whole. By analyzing how symmetries operate near these boundaries, she provided new ways of understanding how information might be preserved, even when classical predictions suggest its destruction, directly addressing aspects of the black hole information paradox. The implications of her work on space-time symmetries extend to quantum gravity, a field seeking to unify quantum mechanics and general relativity. These two frameworks are individually successful, but conceptually incompatible in extreme environments. By identifying conserved quantities in invariant structures at the boundaries of spacetime, Pasterski offered a mechanism by which the laws of quantum mechanics could remain valid even under intense gravitational conditions. This approach does not require abandoning either theory. Instead, it reveals how their principles might coexist in a consistent framework. Her research also emphasizes the universality of symmetry. While some symmetries are apparent only in idealized or simplified systems, Pasterski identified those that persist even under the most extreme conditions, such as near-event horizons or in strongly curved spacetime. These symmetries act as anchors, providing a stable reference that governs the behavior of matter and information. Much like conservation laws govern familiar physical processes in every environment, this universality is crucial as it ensures that the insights gained from extreme cases have broader applicability, informing our understanding of the universe at large. Another significant aspect of her contributions is the interplay between mathematical formalism and physical intuition. While the equations describing space-time symmetries are complex, Pasterski's work emphasizes their physical meaning, showing how abstract mathematical structures correspond to real processes and conserved quantities. This ability to connect formalism with intuition allows her insights to be both rigorous and conceptually clear, making them accessible to other researchers seeking to apply these principles in related problems. Her pioneering research also influences the way physicists frame questions about black holes, quantum information, and gravitational physics. By highlighting the role of hidden symmetries, she shifted attention from solely examining the interior dynamics of black holes to considering how boundaries and symmetries affect overall behavior. This perspective encourages scientists to ask new questions, explore previously neglected aspects of spacetime, and reconsider the assumptions underlying long-standing theoretical models. Moreover, her work demonstrates the importance of precision in theoretical reasoning. Identifying subtle symmetries requires careful analysis, attention to boundary conditions, and rigorous mathematical treatment. Pasterski's research exemplifies this disciplined approach, ensuring that conclusions are robust and consistent with both established physics and emerging theories. This meticulousness enhances the credibility and potential impact of her findings. The broader implications of her research extend to cosmology and early universe physics. Boundaries and symmetries in spacetime are not limited to black holes. They also appear in the context of cosmic horizons and the evolution of the universe itself. Understanding how these symmetries operate under extreme conditions can shed light on the behavior of the cosmos at its earliest stages, influencing theories about inflation, entropy, and distribution of matter and energy. Finally, her work highlights a key principle in modern theoretical physics, that progress often comes from recognizing what remains invariant under change. By focusing on spacetime symmetries, Pasterski identifies structures that persist even when conventional intuition fails, providing a stable foundation for understanding processes that are otherwise mysterious. Her pioneering contributions in this area not only advance knowledge about black holes and quantum gravity, but also offer a conceptual toolkit for tackling some of the most profound questions about the nature of reality. In sum, Sabrina Pasterski's research on spacetime symmetries exemplifies a transformative approach to physics, combining mathematical rigor, conceptual clarity, and physical insight to illuminate the fundamental structures that govern the universe. Through this work, she has reshaped how physicists think about boundaries, information preservation, and the deep interconnections between the laws of nature. Influence on the future of theoretical physics positions Sabrina Pasterski as one of the most consequential young scientists in contemporary research, not merely because of her achievements to date, but because of the enduring impact her work is likely to have on the direction of the field. In theoretical physics, the significance of a researcher is often measured less by immediate results than by the ways in which their ideas reshape questions, frameworks, and methodologies. Pasterski exemplifies this form of influence, guiding the field toward new approaches to long-standing problems and inspiring a generation of physicists to think differently about the fundamental laws of the universe. One aspect of her influence is the way she reorients attention toward foundational questions that have long resisted conventional solutions. Her work in black hole physics, quantum information, and the interface between quantum mechanics and general relativity challenges traditional assumptions and emphasizes the importance of conceptual clarity by highlighting the significance of information preservation, space-time symmetries, and boundary conditions. She encourages the field to address problems not merely as technical challenges, but as opportunities to rethink the underlying principles of physics. This conceptual reframing has the potential to redirect research priorities, prompting new investigations and collaborations that may lead to breakthroughs in our understanding of the cosmos. Pasterski's influence is also evident in the methodological example she sets for future physicists. Her approach combines rigorous mathematical formalism with deep physical intuition, emphasizing both precision and conceptual insight. This dual focus serves as a model for how complex theoretical problems can be approached, illustrating that solving cutting-edge physics questions requires not only computational skill, but also ability to perceive structures and relationships that are not immediately apparent. As younger physicists engage with her work, they are likely to adopt similar approaches, gradually shifting the culture of research toward one that values integrative, principle-driven thinking. Another important dimension of her influence lies in her interdisciplinary perspective. Problems she addresses often sit at the intersection of multiple subfields, including quantum mechanics, general relativity, cosmology, and mathematical physics. By demonstrating the value of crossing these traditional boundaries, she inspires future researchers to adopt broader perspectives, fostering collaboration across areas that historically operated in isolation. This integration has the potential to accelerate progress in understanding phenomena that cannot be fully addressed within a single theoretical framework, such as black hole evaporation, quantum gravity, and the early universe. Her work also shapes the questions that guide the development of future theoretical frameworks by focusing on how information symmetry and boundary conditions interact. Pasterski highlights areas where conventional models are incomplete or insufficient. This emphasis not only points to specific technical problems, but also encourages a mindset in which researchers critically examine the assumptions underlying all established theories. The ripple effect of this approach is likely to influence both the content and the structure of theoretical physics research for years to come. The impact of her research on the broader scientific community further amplifies her influence. Even as she maintains a relatively low media profile, her publications and presentations are widely read and cited among experts. By introducing new conceptual tools and frameworks, she provides colleagues with the resources to explore previously inaccessible problems. This kind of intellectual seeding is a hallmark of enduring influence because it shapes the trajectory of research beyond her own immediate contributions. Pasterski's influence also extends to mentoring and inspiring the next generation of physicists, even indirectly. Young researchers who encounter her work are exposed to a model of how to approach complex questions with independence, rigor, and creativity. Her career demonstrates that meaningful contributions can arise from curiosity-driven inquiry, disciplined analysis, and careful engagement with fundamental principles. This example helps cultivate a culture of thoughtful, principled research, reinforcing the long-term sustainability of theoretical physics as a discipline. Furthermore, her work underscores the importance of persistence in the face of conceptual difficulty. The questions she addresses, such as the reconciliation of quantum mechanics and general relativity, or the preservation of information in black holes, are among the most challenging in all of physics. By successfully navigating these challenges, she shows that progress in theoretical physics is possible through careful methodical reasoning, even in areas that have resisted understanding for decades. This demonstration of intellectual perseverance is likely to inspire others to tackle similarly difficult problems. Finally, Pasterski's influence is evident in the broader evolution of the field itself. Her contributions encourage theoretical physicists to think more deeply about the relationships between laws, principles, and phenomena, emphasizing coherence, universality, and conceptual clarity. Over time, these shifts in perspective may lead to new theoretical breakthroughs, the development of unified frameworks, and a deeper understanding of the fundamental nature of the universe. In this sense, her influence extends beyond specific discoveries to shape the very methodology and mindset of future physics research. In conclusion, Sabrina Pasterski's influence on the future of theoretical physics is multifaceted and profound. Through her focus on foundational questions, methodological rigor, interdisciplinary perspective, and conceptual innovation, she is guiding the field toward new ways of thinking and inspiring a generation of physicists to pursue deep transformative insights. Her work ensures that her impact will persist not only through the ideas she generates, but also through the intellectual culture she helps cultivate, shaping the trajectory of theoretical physics for decades to